Thank you. Also, thank you very much for the opportunity to present here and the invitation. So, as said already, obviously, I'm from the company Zurich Instruments. We are based in Zurich, and my name is Moritz Kirste. So, what do we do in quantum computing? Well, we provide classical instrumentation for quantum computers, so that means we provide control electronics. And together with that, we also have a quantum mission. And we say we want to accelerate the second quantum revolution and help to build quantum computers. Now the question would be, how do we define now success in our quantum mission? And we define our success by saying that our customers can focus on their most relevant task, which is doing cutting-edge research. And you can see here a very nice result from the ETH Zurich, where two scientists have just published a Nature paper. It's actually the Surface 17 paper, in which they have proven the first logical qubit on a superconducting qubit. And these customers here, or these partners, I would rather say, they have been successful in their task, and by this, we have also been successful in our quantum mission. Now, there's a lot of talk always in the community at the moment about scaling to high qubit numbers. And you can also say the road to quantum advantage really leads to these large qubit systems. But to reach large qubit systems and large qubit numbers, we first have to make sure that we understand and work on the right qubit technologies. We also have to make sure that we have global systems and central control in which we can learn, for example, quantum error correction on these smaller qubit numbers, and then use this learning for scaling to larger qubit systems and these distributed systems, which then can really, in the end, guarantee fault-tolerant quantum computing and quantum advantage. And in my talk, I would like to give you a couple of examples from the world, also very much focusing on Korea, some examples of how our partners are on the roadmap to this quantum advantage. Because we believe to really fulfill this, we need to be able to do quantum error correction, we need high fidelity, both on the control side and on the readout of qubits, and we need to be ready for scaling. So let's start with the very first example, quantum error correction. This is actually not from our partners. This is one of the examples we did ourselves in-house. What we have done here is we have simulated on our FPGA directly an implementation of a union-find decoder, as you can see there in the reference, or taken from that reference. You can see here our central device and the center of our control electronics. There's an FPGA inside, and we could, in the end, test or find out that the resource use on the instrument for certain distances is really useful, or it can be implemented with just enough resources on the device. But what's even more important is, in the end, the decoder throughput. Because a decoder can only be fully functional if the decoder time is much smaller than the cycle time you're using in your algorithm. And you can see here that our decoder can be executed in 20 nanoseconds, while the cycle time is 0.5 microseconds. And all of this adds up together to the T-gates of 4.5 microseconds, decoder plus latency of 0.9 microseconds. So by this, you can see the implementation of the T-gates is much longer than the implementation which is needed on the decoder. Why is that important? If you can't guarantee that, your need for decoding builds up with every cycle, and then your needed decoding time would increase exponentially. So with this, we can show decoding is possible on our FPGA. But let's look into doing this in real time. So this is an example from ETH Zurich. So this is not direct quantum error correction, but it's a success story of showing adaptive control using real-time feedback. So it's an experiment with a mid-circuit measurement, and with the mid-circuit measurement, there's a real-time feedback, which then led to a feed-forward time, including the recovery pulses of 928 nanoseconds. It was realized on a 17-qubit chip, and again, This is not direct quantum error correction yet, but it's the first time it was ever proven on a commercially available control system that you can do real-time branching within the qubit lifetime. So let's leave quantum error correction and let's go to fidelity. I said fidelity, both on the control and the readout, is also very important to really reach quantum advantage. So the next success story I would like to share with you is coming from Japan. In this case here, we are looking at results from Professor Nakamura. And what they were able to do is, in the end, measure on their device world record 2-qubit gate fidelities of up to 99.92 on a CZ gate. And this was possible by two things. First of all, with our pulse properties on our very low signal-to-noise ratio hardware, and also with a fast data exchange where they were optimizing their pulses directly with some machine learning and being able to upload new pulses very fast to our devices. Let's look at another example of fidelity. This is now not on the control side, but this is on the readout side. And this is a project together with SKKU, Withwave, a Korean company, and EPFL in Switzerland. And it's a project which focuses on a novel tuba design. So instead of driving a tuba with a continuous wave, in this case, the idea is to drive a tuba with a pulse. And you can also see, or already see here, some nice results from this work, where you can really prove that you can improve the readout fidelity, and we are very much looking forward to new results from this project. I also said scalability is important. And regarding the scalability, I would like to share a success story or one of our partnerships with Chris here in Korea. Chris comes next. This is with SKKU still. Sorry about that. Chris comes on the next slide. So this one is with SKKU. And the idea here on this one is also increasing the number of readouts you can do on a single qubit line. So what the lab of Professor Yonok Chong at SKKU has done here is they have created a device which has 9 qubits on one single readout line, as you can see here. And what you can also see here is a very nice measurement of all these 9 qubits in one single resonator spectroscopy, with a nice picture of the lab. And again here, why is this possible? Because of the capabilities of our control electronics to, in the end, being able of reading up to 16 qubits on the single readout line with a very low signal-to-noise ratio. Now, as promised, comes the example of scalability from Chris. So in this case here, what is Chris doing? They are looking into having high QPU or large QPU productions and QPU characterization. And together with them, we share our experience on bringing up and maintaining large QPUs and characterizing these. So in the end, we are sharing our expertise on operating large quantum computing systems, the characterization, and then also the software development. And how do we do that? Well, in the end, we send our researchers to the lab at Chris, and we understand or try to understand more and more and better how they are working with our devices, how they do the characterization. And we also dispatch the 3 PhD-level researchers directly from Chris to us in the company, to our headquarters. So this collaboration is going on quite well. We provide into it our technology-leading hardware for quantum computing, and Chris, in the end, helps us in this characterization protocols, in the software development, and in the next steps, we want to focus in our project on error mitigation and on quantum error correction, and also on automation workflows. Because that's the last aspect. Remember, I said at the very beginning, on the roadmap to quantum advantage, we need quantum error correction, we need the high fidelity, and we need to do scaling. But if you really want to do scaling, you need some kind of automation, because imagine 1,000 qubits, it actually already is a problem with 20 qubits. If you do, in the end, characterization of all these as a manual work, this is a tough job. So together with Chris, we are working on the software to do automation. And what we offer in our Lab1Q open source software framework is means to do automation. So we have elements in there, or we have parts of the software which we call the quantum elements, the calibration workflow, and something which is a directed acyclic graph. And these quantum elements, in the end, they define what the user wants to calibrate. So let's say, for example, the readout resonator frequency. Then in the calibration workflow, the user have a very easy way of defining their experiment, how in the end it is done, how it's updated, how certain parameters are changed, how parameters are saved to a database. And all of this is then integrated in a directed acyclic graph, a DAG, with some kind of graph runner to use machine learning on the graph to decide whether one of these parts, one of the nodes of the graph is either fulfilled or not fulfilled, if you can transverse through the graph, or you may, well, if it's cyclic, you don't go backwards, but when to pass to the next node. Now, for this, I also would like to show you one result. So this is now not with a Korean partner. This is now, again, with a European, actually a German partner. So this is the WMI in Munich, the Walter Meissner Institute. And what we could show here, so this is only part of the acyclic graph, which I was talking about before. So it's not the full graph. And what you see here, each of these nodes corresponds to one important experiment in the characterization of each of the qubits. And since our software is fully parallelizable, we could, together with active qubit reset in each of the experiments, we could tremendously speed up this process of characterizing a full QPU. We could show that we have sublinear scaling in time with the number of qubits, and could show that on a 17-qubit tune-up, we take less than 20 minutes to tune up the full chip. Important caveat to that, that does not include 2-qubit gates. That's just single qubit gates on these 17 qubits, but still I think it's very important to note, if you now think about this and you go to higher qubit numbers, that again, the most important message is it's sublinear scaling. Now with this, I'm also already coming to an end. So to summarize again, if you really want to reach quantum advantage, it is again the quantum error correction, the fidelity, and the scalability that counts. The control electronics we provide are used for controlling quantum computers, and together with our partners, we have success in all these areas, and we keep on driving this success with the partners together. If you want to talk to us about it, or you want to learn a bit more about the instruments, come by at our booth. B15 is just right next to the coffee area at the very end of the hall here, and I would like to thank you all for your attention.